My dear viewers, I hope you are doing well. Welcome to our today's class. It's our second lesson on the topic Hooke's Law. So as usual, let me commence by giving you the quote of the day, which states that be happy for other people's success because their success won't limit yours. So we'll discuss that quote at the end of our class today. So today we are looking at the area under force versus extension graph. So in short, we are looking at the work done under a force versus extension graph. Now to find the area under graph, remember the area under graph usually means, for example, if this is our graph, then when we talk of the area under the graph, it is actually this particular region or this particular area which is below that line or below our graph. So this shaded region is what we are calling the area under our graph. Now the area under the graph, if you study this area well, that is the shaded region, it is in a triangular shape. It is in a triangular shape. So that means if we want to find the area under that graph, we'll simply find the area of the triangle, the area of the right angle triangle. Actually, this is a right angle triangle whereby our 90 degrees is somewhere here. Now, the area of the right angle triangle is given by a half base times height or a half height times base. So if we look at our diagram, what is representing our height? Remember, the height is usually the vertical dimension. What is on our vertical axis is actually the force which is in Newton. So the height in this case, that is the height represents the distance from this point up to the upper part. And when we are moving along this axis, we are actually moving along the force axis, and therefore our height in this case will be the force. So the height is our force, and the extension in this case represents the base. Remember, the base is usually the horizontal dimension or the horizontal length or the horizontal distance. Now in this case, for this right angle triangle of ours, the base represents the distance from the origin or from this point up to this other end. And if you look keenly, this distance is actually the extension. So the base in this case is our extension. Therefore, we can easily relate that the area of the triangle or the area under the graph, which is equals to a half base times height or a half height times base, is equals to a half. The height is the force because this is our height. We are moving along the force axis. So the height is our force and the base or the horizontal position is our extension. Therefore, the base is our extension. So we let this one to represent our equation 1. Now remember that the area under the graph will always be equal to the work done in stretching the spring. So the area under the graph is equals to the work done in stretching the spring. So in short, you are saying that this area under the graph, which is a half force times extension, is equals to the work done in stretching the spring. We can also express this equation in another form, that is by substituting the Hooke's Law equation. Remember, the Hooke's Law stated that force will always be equal to Ke, where K is a constant that is representing the spring constant, E is the extension, and F is the force. Now, if we substitute force is equals to Ke in our equation 1, remember equation 1 was a half force times E. So the region or the point where we have F, we will substitute with Ke. That is the spring, the product of the spring constant and the extension. So if I substitute the work done, that is the force is equals to Ke in the equation of the work done, we will have the work done in stretching the spring being equal to a half Fe. Remember, a half Fe is just this equation here, a half Fe. So we are substituting the force is equals to Ke. So in the region where we have force, we are replacing or substituting with the spring constant and the extension. Therefore, this equation will become a half F is actually Ke, then times this extension that was here. So we'll have a half Ke times the extension. Now remember, the product of extension and extension, it will give you the square of the extension. Therefore, the work done will be equal to a half the k that was here times the square of the extension. So we are also saying that the work done in stretching the spring can also be given by a half times the product times the spring constant and the square of the extension. So there are two formulas for finding the work done in stretching the spring. So the first one is that the work done is equals to the area under the graph, which is equals to a half force times extension, which can also be given by the work done is equals to a half times k times e squared. So remember, we are saying that the work done is equals to the area under the graph, and we are giving the area under the graph as a half force is equals to a half fe, because this area is in triangular shape. It is a triangular shape. Remember, if the area was in maybe a different shape, for example a rectangle, we will find the work done as the force times extension, because the area of a rectangle will be length times width, and the length in that case will be maybe the extension and the height maybe the force. So in that case, the work done will be Fe, that is force times extension. If the area under the graph was maybe in a trapezium shape, the area or the work done will be equal to the area of that trapezium. So what determines is actually the shape of the area under that particular graph. So if the area is in a rectangular shape, then the work done will be equal to the area of the rectangle. If the area is in a square shape, then the work done will be equal to the area of the square. If the area is in a trapezium shape, the work done will be equal to the area of the trapezium, and so forth and so on. Therefore, we are concluding that the area under a force versus extension graph is equal to the work done in stretching the spring. Also remember that whenever we talk of force versus extension, it means the force will always be on the vertical axis, and the versus or the extension will always be on the horizontal axis. So next we look at an example, that is of how to find the spring constant and the work done in stretching the spring between points BC and AC when given a force versus extension graph. So from our figure here, we are required to use the graph to determine A, the spring constant. So remember, earlier on we did say that the spring constant will always be equal to the gradient of the force versus extension graph, or the slope. So we are saying that the spring constant will be equal to the gradient of the force versus extension graph. Now for us to find the gradient of this graph, we need to identify 2 points. So remember, mathematically we did say that the gradient, if this was the y-axis and this is the x-axis, then the gradient will be equal to the change in y over change in x. But what is representing our y-axis here is the force, and what is on our horizontal axis here is the extension, and therefore the gradient or the spring constant or the gradient of the graph will be equal to the change in y, but the y is the force, so it will be change in force over change in x. The x or the horizontal axis is having the extension, therefore the spring constant will be equal to the gradient of the force versus extension graph, which is equals to the change in force, because the force is on the vertical axis, divided by the change in extension, because the extension is on the horizontal axis. Now if I may identify 2 points to use for calculating my area or for calculating the gradient of my graph, so I'm identifying 2 points, and my first point is point C. I'm taking point C and point A. Remember, when you are finding the gradient, so long as it is a straight line graph, you can pick any 2 convenient points on that line. If you pick any 2 convenient points, actually we expect the gradient to be exactly the same. So like for this case, I'm picking point C and point A. Remember, point A is the origin, which is 0, 0. Then point C is 0.4, 20. So remember, 0.4 is the extension, which is in meters, and the 20 is the force, which is in newtons. So to find the gradient it will be change in force divided by change in extension. So to find my change in force, I will take the value of force for point C, which is 20, then I less or I subtract the value of force for point A, which is 0, because at this point actually no weight is attached and therefore no force is being applied on the spring, and therefore the extension is also 0. So the change in Y, which is the change in force, is 20 minus the change in force at this point is actually 0. So I'll have 20 newtons minus 0 newton. Then divided by change in X, or change in the horizontal axis, I will have the change from this point up to this other point. So the change in X will actually be 0.4 minus 0. That is this particular distance here. So I'll take 0.4 minus 0, which gives me 0.4. Then 0 minus 20 minus 0, you also get 20. So after that, you take 20 divided by 0.4, you'll actually obtain 50. Now remember, the force was in Newton and the extension was in meters. So I'm taking Newton divided by the meters. So Newton divided by the meter, I'll get Newton per meter, which according to the laws of indices can also be represented as Newton meter power -1. Power -1 simply means Newton divided by the meter. So that is how we find the gradient. Remember, another person could have chose to use maybe point A and B. So if you use point A and B, the gradient will be change in Y, or change in force divided by change in extension. So that will be change in force. You will simply take 10 minus 0, then divide by change in extension, you'll take 0.2 minus 0. So you take 10 divided by 0.2, you'll actually obtain, you'll still obtain the 50 Newton per meter. Another person could have chose to use maybe point C and point B. So in that case, the gradient will be change in force over change in extension. So for the person who used point B and C, the gradient will be 20, change in force will be 20 minus 10, which is actually 10, then divide by change in 0.4 minus 0.2, which is 0.2. So you take 10 divided by 0.2, you will still obtain 50 Newton per meter. So regardless of the point that you pick, actually the spring constant or the gradient of the graph will exactly be the same. So part B, they want us to find the work done in stretching the spring between point Roman 1 BC. So we saw that for point BC, the work done will always be equal to the area under the graph. So the area under the force against extension graph will always be equal to the work done. So for Roman 1, they want us to find the work done between point B and C. So between point B and C, actually the work done, the area under that graph between point B and C is actually this area. That is the area B, C, D, E, and back to B. So they want us to find this area. The area under the work done is equal to the area under the force against extension graph. And since they want us to find the area or the work done between points B and C, it means they are talking of the area under B and C, which is actually this area here. That is area BC, D, E, and back to B. So if you study this figure well, it is actually a trapezium. So this figure is a trapezium. That is area BC, D, E, B is a trapezium which has parallel sides B or parallel sides D, C, and B, E or EB, and the height is actually ED. This is our height, and these are the two parallel sides of the trapezium. Now remember, area of the trapezium is given by a half into bracket A plus B times height, where A and B are the two parallel sides, and H is the height between, or the vertical distance between those two parallel sides. That is the parallel sides AB. So like in our case, the parallel side A represents the distance DC or CD. Then B represents the A actually represents our distance BC, and B represents the distance DC or CD. Then the H represents the distance ED. So clearly from our diagram, the area will be equal to a half into bracket A. So A is the distance from EB. So that represents, this is actually along the vertical axis. So to find distance EB, or what is our A, we'll take actually 10 minus 0, which is actually 10 Newton. Then to find our distance B, that is the other parallel side DC, this distance will be the distance from 20 Newton minus the 0. So 20 minus 0, you actually obtained 20 newtons. Then the height, remember the height is the distance ED, that is the height of this particular trapezium, or the vertical distance between the two parallel sides BC and CD or DC. So the height represents this distance, or the height of the trapezium, this distance H, or this distance ED. Then the distance ED, we are moving along the horizontal axis, or the extension axis, which will be equal to the distance from point D, the distance of D from E. So remember, D is at 0.4 meter, then E is at 0.2 meter. So to find this distance, we'll simply take 0.4 meter minus 0.2 meter, which is actually 0.2 meter. Now you take the sum of 10 and 20, you obtain the 30 Newton. So that the area will be equal to a half times 30 times 0.2. Now remember that if you take this 0, we'd remove this decimal point, so that you have 3 times 2, which is actually 6. So 6 divided by 2, you'll obtain 3. So remember, the units will be Newton meter, because this was force, which was in Newton, then this was extension, which was in meter. So you take Newton times meter, you'll obtain Newton meter. So the work done will be 3 Newton meter. So later on, we'll see that the work done is usually given by the force times the distance. In this case, the force is the force that is applied on the spring, and the distance is actually the extension of the spring. Then Roman 2, they want us to find the distance, the work done in stretching the spring between point A and C. Now remember, from point A and C is actually the total distance, or the graph for the whole experiment. So the work done will be equal to the area under the force versus extension graph, and the area in this case, the area from AC. So the area under the graph is actually this particular area here, that is the area A, C, D back to A. So that this is the area under the graph. So if you observe this area keenly, it is actually the area of a right angled triangle. That is the right angled triangle A, C, D, A, and the 90 degrees will be at point D. So the point D, that is where we have our 90 degrees. Then, since we have seen that the work done is the area under the graph, and the area under the graph is the area of the triangle ACD, we know that the area of the triangle is a half base times height. The height in this case is actually this perpendicular distance, which is representing the force, because we are moving along the vertical axis. So this particular distance is our height, and the base, of course, is the this particular horizontal distance, that is distance AD, and we are moving along the extension axis. So the work done will be FE, that is base times height, or the force times the extension, because F is our height and E is our base, or the extension is our base. So the force, that is the force from AC, it will be the distance DC. So DC, to obtain that distance, you simply take 20 minus 0, which is actually 20. Then the distance E, or the extension E, will be the distance AD, which is 0.4 minus 0, which is still 0.4. So 2 divided by 20, you obtain 10. 10 times 0.4, you'll obtain 4 Newton meter. Alternatively, we also derived another formula for finding the work done. And the formula was that the work done will be equal to a half KE squared. That is where K is the, of course, the spring constant, and E is the square of the extension. So alternatively, you can also use this formula, and you are seeing that for that case, the area the work done will be a half Ke squared. K is the spring constant. Remember, we have already calculated the spring constant. We found it as 40 Newton per meter. So the work done will be a half times K, which is 50, then times the extension. Extension for the old graph is actually 0.4 minus 0, which is actually 0.4. So, but because it is a square, it will be 0.4 times 0.4, which will actually give us. So remember, you take 0.4 times 0.4, then you multiply by 15, then divide by 2. If you perform this one using a calculator or by simple cancellation, you will actually obtain 4 Newton meter. So notice that this value is exactly the same as the one that we have obtained up here. So you can either choose to use this formula or use these other formulas, and the results will be exactly the same. Remember, in physics, formulas usually earn you a mark. So it is very important to include the formula whenever you are calculating, you are performing any calculation in physics, and also remember to work with the SI units. So remember, for this case, 50 is in Newton per meter. So Newton per meter times extension is in meter, but it is extension square. So Newton divided by meter times meter square. Actually, the 1 meter will cancel with the 1 meter, so that you remain with the Newton meter. So it will be 4 Newton meter. Lastly, I have an exercise here to help you reinforce the ideas that you have learned. So the exercise reads that the table below shows values of extension of a spiral spring that obeys Hooke's law against various forces. So you're required to use them to answer the following question. So these are the values. So part A, you are required to plot a graph of force against extension. Part B, you are required to use the graph to determine the spring constant. So I've done it, and I expect your answers to be 4 Newton meter. And for part C, determine the total work done in stretching the spring. I've done that, and the expected answer is 800 Newton meter. So actually try doing this practically and see whether you obtain similar values as mine. And in case you are having challenges in handling this exercise, feel free to drop a comment in the comment section of this video. And of course, as usual, I'm always there to try and help where necessary. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that, "Be happy for other people's success, because their success won't limit yours." So what does this particular quote mean? So the quote is warning us against being jealous for other people's success. And always remember that another person's success does not make you successful. Always remember that another person's failure does not make you successful. And another person's success does not make you a failure. And therefore, feel free to celebrate other people's success, so that when your time for succeeding comes, they will also celebrate with you. And lastly, the dictionary is the only place where success comes before work. But in real life, the latter supersedes the former. That is to mean, in the dictionary, it is the only place where you will find success coming before the word work. But in real life, actually, the work comes before the success. The work comes before the success. So we actually through with our lesson. I thank you for always coming back to my channel to view my lessons. I actually don't take it for granted. And I also humbly request you, for those who have not subscribed, actually feel free to hit that subscription button. It really does help me to grow the channel. And also, if you enjoyed the video, feel free to like the video, and also to hit the notification bell, so that whenever I upload a new video, you'll be the first person to receive a notification. Thank you. I wish you all the best. Until next time.